Welcome back. Here we are in part C of our presentation. In this part, we're going to learn everything we need to learn about galvanic cells or batteries. So we're going to learn the terms associated with electrochemistry. It's the production of energy in the form of electricity from chemistry reactions. And we're going to see how we construct and operate a galvanic cell, which produces energy. And we will briefly talk about electrolytic cells, which consume energy. And we're going to begin with the galvanic cell. And the model we're going to use, this is the, this is the very basic model. The model we're going to use is we're going to have two cells that are going to work together. In one of them, we're going to have the reduction happening. In the other one, we're going to have the oxidation happening. And I'm going to show this to you by doing a random example. I'm just making this up as I go, so I can tell you all the different parts of the galvanic cell. So the first thing we have is two containers. Then we are going to put a piece of metal in the container. So we're going to put a piece of metal inside the container and another piece of metal inside the other container. And then we're going to say this, like I told you, these are pieces of metal. So I'm just going to randomly pick, I'm going to say that this one is a piece of copper. And this one is just a piece of, let's say, zinc. And if you remember from Chem 1411, we mentioned that metals always like to lose electrons. When we talk back then, when we talk about metallic character, one of the things we said that makes something more metallic is the fact that it can lose electrons easier. So what we're going to do, we're going to connect these two pieces of metal with a wire, and in between, we're going to put something where we can measure voltage. So we're going to be measuring volts with that meter. And like I told you before, metals like to lose electrons. So this metal is going to lose electrons. And this metal is going to lose electrons too, because both of them are metal. Both of them want to lose electrons. However, there is a problem. They're going to be traveling in opposite directions. When they meet together, they're going to repel each other. So that cannot happen. What's going to happen here is that one of the metals is going to be more powerful than the other. One of the metals, it would be more prepared, or it would have a higher tendency to lose electrons. And we can do that based on the radius of the element, right? If they are on the same group, the bigger one will lose electrons easier. So one of them is going to have to take electrons. So let's for right now think that copper is the one that is going to win this discussion. So we're going to assume for right now, this is probably not true. Remember, I'm making this up as I go. We're going to assume that the copper is going to win. Therefore, the copper is going to push the electrons all the way through toward the zinc. However, those electrons are going to try to find a place, and this is pure zinc. We're not talking about a cation that can take electrons. We're talking about pure zinc, so the electrons are not going to be able to get anywhere. There's no place for them to land. However, those electrons are coming. There's no way to avoid that. So what we're going to do to prevent that problem, because if not, they're going to get stuck in there, we're going to add a solution to the beaker. So this solution, so obviously an aqueous solution. To make everything easier, since we're dealing with zinc, we're probably going to put in there something like zinc chloride, which is a solid, but when I put it in water, it's going to go into zinc 2 plus and chloride negative. So this solution, which is an aqueous solution, is going to contain zinc 2 plus, chloride, zinc 2 plus, chloride, chloride, and chloride. So there's 2 chloride for every zinc 2 plus. However, on this particular situation, the chloride is not going to be a player. So for the purpose of clarity, I'm going to designate those spectators. So they're there, but we don't care about them. I'm going to have a lot of zinc 2 plus. So this solution is going to contain a lot of zinc 2 plus. And I'm using a compound of zinc because I'm using zinc. So I want to keep everything kind of more or less homogeneous. So what's going to happen? Assuming, remember, we're doing this under the assumption that the copper can win on the push of electron, that the copper will be losing the electrons easier. Assuming that, what's going to happen, these electrons are going to sense that there's something positive out there, and the electrons are actually going to come out of the metal. Remember, metals are conductive, so those electrons are going to go through there, and they're going to search on those zinc 2 plus that are in contact with the metal. Therefore, the electrons are going to go there, and what's going to happen is that the zinc 2 plus is going to be reduced, producing more zinc. And you can expect the bar that we put in there, as time goes by, is going to get bigger, or not get bigger, but the mass is going to increase, because whatever is in contact with the solution, when the zinc gets reduced, it's going to become the metal, and it's going to stick to the bar. So we can see how on this particular site, reduction is happening. And since the electrons are leaving from the copper, right? Then this is nothing more than the copper losing electrons. And we're going to say that this is copper losing 2 electrons, becoming copper 2 plus. Which means we're going to have another aqueous solution over here. So that this copper can become aqueous and be on the solution. So what's going to happen here, as the electrons leave, the copper 2 plus is going to go into the solution. And therefore, oxidation is happening here. So notice this. As the copper loses electrons, the bar that it used to be bigger is going to start becoming smaller because it's losing copper, and the copper is becoming part of the solution. However, the solution, which was neutral, now is becoming more positive. So the positive character on this beaker is increasing. On the other side, on the reduction side, we are removing zinc. The zinc is becoming, the zinc 2 plus is becoming zinc solid, and the bar is getting bigger. So on this side of the solution, the positive character is going down because we're removing zinc plus from the solution. So for these electrons to move, we're going to have to create a circuit, just like in electricity. If I have a light bulb and I have two connectors there, and I apply electricity to it, nothing is going to happen. However, if there's a filament there, then the light will go bright because we are completing the circuit. So electricity goes in, goes through, and we're completing the circuit. So the same thing had to happen on electrochemistry. The battery has to have a circuit so that the electrons can travel. So the way we're gonna do that is by putting a connection here that goes from one beaker to the other, and we're gonna put some type of salt that is soluble, and look what happens. I told you that on the left side, the positive character is increasing. So to bring that back into balance, just like Le Chatelier's principle, we're gonna bring the positive charge down to get it back to where it's supposed to be. So that means the nitrate, which is negative, is gonna travel toward there, therefore bringing down the positive character. In a similar fashion, where the positive character is decreasing, then we're gonna bring more positives. So the K plus will travel there to bring the positive balance back up. This particular part of the cell is what we call a salt bridge, because that's what it is. It's a bridge connecting one beaker to the other, one compartment to the other. So this way, what we have is a flow of electrons coming through there, going in, continuing the charge of movement of charge toward through the salt bridge, and connected there. So we completed a circuit. So the concept or the thermochemical terms that we talked so far are the fact that you have oxidation on the left side, reduction on the right side. There is a salt bridge. There's a voltmeter that we can use to measure the current or the voltage that is going through. And there's one of the metals that is losing electrons, and there's one of the metals that is gaining electrons. The metal that is gaining electron, we're gonna call that the cathode, And the metal that is losing electrons, we're going to call that the anode, because those electrons made this the negative end. The fact that there's a potential of those electrons in there just waiting to be connected to live. And the cathode is the one that the electrons are being directly pumped into it. So electrons are following the positive side because negative love positive. So kind of overall, those are the terms that we need to do. However, let's go back to the beginning. So going back to the beginning, let's make sure that we understand what we're doing and why we're doing it. So I'm going to introduce now another term that is called reduction potential. And this story began because we had a bar of copper on one side and a bar of zinc in the other side. So the reduction potential is basically a measurement of the tendency of the metal to be reduced. The higher that number, the easier it is to reduce that metal. And the way we get this is we do experiments when we have two beakers. We have a piece of metal, let's call this metal number 1, and we have hydrogen on the other side. So we're going to use hydrogen as our reference, and whatever voltage we can measure in between these two, that's what we call the reduction potential. And we tend to do that we do that experiments at standard conditions. On this case, 25 degrees Celsius and 1 atmosphere with 1 molar solution. Remember, there's going to be a solution on each one of these. So when we do standard conditions, we're talking about 1 molar of the solution, 25 degrees Celsius, and 1 atmosphere. So when we do that compared to the hydrogen, whatever voltage we get, we call that the reduction potential of that particular metal that we're talking about. And by doing that, we can generate tables with information that we can use. And you're going to see tables like that. For example, this tells you that the reduction potential of let's see what would be a good example. The reduction potential of silver 2 plus, we're starting with silver 2 plus. The reduction potential of silver 2 plus is 1.98. And it also tells us that the reduction potential of silver plus 1 is 0.80. So this tells me that it's easier to put an electron in Ag2 plus than on Ag plus. And does that make sense? Well, Ag2 plus and Ag plus have the same amount of protons, right? So the nucleus is the same strength on both of them. But Ag2 plus don't have to worry about maintaining 2 electrons. So the nucleus, it can concentrate the force more than an Ag plus, where it still has to worry about all the electrons, 1 more than the Ag2 plus. So it makes sense that the pull of the neutron on Ag2 plus is stronger than on Ag plus. Therefore, we have a higher reduction potential. And why does that matter? Because when we go back to our table, me to our problem, we're going to have to compare copper 2 plus gaining electrons versus zinc 2 plus gaining electrons. Because remember, if this is zinc, my solution is going to contain the cation of the zinc. If this is copper, my solution is going to contain the cations of the copper. And like we mentioned before, if copper is the weakest one, then the electrons are going to come that way. If zinc is the weaker one, then the electrons are going to come that way. So before, I just told you to assume that the copper was the stronger one and the zinc was the weaker one. Now we have data we can use. So we're going to see which one of these can take the electrons easier, and that's where the electrons are going to go. So let's find copper 2 plus. So the reduction potential for copper 2 plus, not on this table, probably on this table right here, the reduction potential for copper 2 plus is 0.34. volts. The reduction potential for zinc 2 plus, let's see if we can see it here, is going to be negative 0.76. So this tells me that copper can be reduced easier than zinc. So if someone is going to receive electrons between these two, it's going to be copper 2 plus. So that tells me that if I connect this with a wire and I put a voltmeter right on the center, I'm going to see a movement of electron with a overall cell potential where the electrons are going to go toward the one that can be reduced easier. So the electrons are going to go that way. So this is the way the electrons are going to go. And we're going to call this the electrochemical potential, which is measured in volts. And a volt is a joule per second. So it's energy. So if instead of a meter, I have an electric motor in there, then the electric motor will start working because there's electrons going through it. So it's generating electricity. So once more, we look at the cation of the two metals that we're comparing. We find on the table the reduction potential. The one with the bigger reduction potential can be reduced better. It has the potential to be reduced. And that's the one that is going to receive the electrons. So as the electrons travel through the metal, they're going to come out into the aqueous solution. They really don't come out. The copper that is in contact with the metal, the copper 2 plus, will gain those electrons and become copper solid. And therefore, you start getting copper solid deposit in top of the other copper solid. And it start increasing in mass. So, the electrons are always going to travel toward the one that can be reduced better. So, reduction is happening here. and oxidation is happening here. As the electrons leave, then more zinc gets broken off the metal. They're becoming aqueous. So the place where the oxidation happens, we call that the anode. The place where the reduction happens, we call that the cathode. And an easier way to remember this, oxidation begins with a vowel, anode begins with a vowel. Reduction begins with a constant, cathode begins with a constant. So we have defined the anode and the cathode, and the electrons will always travel. Just a reminder, because you know if it's oxidation, the electrons are leaving. The electrons always travel, what I like to say, alphabetically. It goes from A to C, from the anode to the cathode. And the cathode is the one that is going to be the positive one. And the anode is the one that is a negative object. So that will be the one which is negative. This will be the one which is positive. And like we discussed before, for this to be a complete circuit so that the electrons can move, we're going to have to put a salt bridge right into the solution. This could be a piece of a tubular glass with something on the inside, or it could be a piece of paper saturated with some type of salt. And we're going to fill it up with potassium nitrate, for example, something that will dissolve, some ionic compound that can dissolve in water. And since on the cathode where the reduction is happening, here where the reduction is happening, the cation is becoming part of that, so we're losing positive charge. So the cation, which is potassium in this case, will travel to bring that positive charge back again. On the anode, where a cation is becoming part of the solution, so it's leaving the metal, then we're going to bring the nitrate with a negative charge to balance with the extra positive charge that we're having. So that's the function of the salt bridge, is to regulate and keep the balance charge the same on both sides. So we talk about the cathode, where the reduction happens. We talk about the anode, where the oxidation happens. And all we have left to do is to calculate what would be the voltage of this cell. And the way we do that is the electrochemical potential of the cell is going to be the electrochemical potential of the cathode minus the electrochemical potential of the anode. On this case, the cathode is the copper, so 0.34, and the anode is the zinc. Notice that this equation and this equation are both reductions. We know that reduction happens in one of the cells and oxidation happens on the other cell, but for the purpose of this formula, we write down both values for reduction because this negative symbol is changing the value. So for example, the zinc is going to be minus 0.76. So having a negative, it makes it positive. So do not flip those values. Do not say, oh, this is the anode, so this is going to be oxidation. So do not flip the values. The formula takes care of that. The cathode minus anode takes care of that. Do not flip those values from the table. Use the values from the table exactly as you get them from the table. So when we do that, we said that the total electrochemical potential for this cell is going to be 6 plus 4 is 10, 3 plus 7 is 10, you got 1, so 1.10 volts. So if this was a test, I would expect for you to put 1.10 volts because I was able to do the calculation. And ladies and gentlemen, this is how we construct a galvanic cell that is going to produce energy. How do we know it's producing energy? Because we got a positive value, which also tells us that this is a spontaneous reaction. If I have a piece of copper in a solution with another piece of zinc on the other cell on a solution, and I connect them with a cable and a salt bridge, I will get a voltage going. If I have a light in here, the light will be bright because there's electricity going through it. So this is another thing. Once you do these calculations, having electrochemical cell potential positive tells you that this is a spontaneous reaction, and by definition, it will happen on its own. And these are the tables that are going to be on your appendix at the end of the book. So quick review. Here you have a better representation. So it tells us what the electrochemical cell is, voltaic, which is the same as galvanic. It tells you also that the oxidation happens at the anode. O goes with A. The anode is where the electrons are coming from, and it's negative. And the cathode is where they're going to, where they're sinking. And reactions in voltaic cells are product favorite reaction, which means that the equilibrium constant is bigger than 1, delta G is negative, and now you know that the E of the cell is bigger than 0. And like I told you before, batteries are voltaic or galvanic cells. And the electrons, they always travel from the anode to the cathode, alphabetically, always from A to C. So here you can see a little a more detail. This is how we get the tables. Those tables come because we have a setup where one of the side is hydrogen. So we're gonna determine hydrogens to be a 0 voltage. So E of the cell is gonna be E of the cathode minus, let's see, the electrons are traveling this way minus, so before I say that, we see that the electrons are traveling that way, right? So they're gonna sink into that. So this is my cathode, right there, right? And the electrons are coming from here. So this is my anode. So E of the cell is gonna be cathode minus the anode, on this case, the reduction potential of zinc. So we're using hydrogen at the standard, so that's how we build those tables. And you can see what I was trying to show you earlier. The electrons are leaving the zinc. Let me show it to you here. So this is how the oxidation is happening. The electrons are leaving the zinc. Therefore, the zinc is becoming zinc 2 plus, which goes into the solution. So the positive character here is increasing because we put in more cations in there. And we can see the same thing happening on the anode. On the cathode. The electrons are coming this way. And as soon as they come into contact with something positive, then the positive is going to come down. And you're going to be creating hydrogen gas. So make sure you understand what's happening at the atomic level on each one of them. So those were the voltaic cells. So this is the voltaic cell producing a voltage. The electrolytic cell, you apply a voltage to it. So we're using a battery to cause a chemical reaction. And we use this a lot for electroplating, to chrome something. So you take a piece of iron and you put it on an electrolytic cell. You can make it really shiny by depositing a chromium on top of it. So for right now, just be aware, we're not going to go too much into detail until we do a lab, one of the labs that we do toward the end. For right now, just know that an electrolytic cell consumes energy. It needs an energy source. The galvanic or voltaic cell produces energy from a chemical reaction. And this is something, so do we want to be doing all this drawing all the time? No, we're going to use something called the shorthand description. So this is so you're going to have two lines in there separating one side from the other. If you notice, this one represents going from zinc to zinc 2 plus, which means you're losing 2 electrons. So this is my anode side. And this one, you go from copper 2 plus to copper. So you gaining 2 electrons. So this is my cathode side. So if I were doing a drawing of this, I will do something like this. I will have 2 beakers. In one of them, I will have copper and copper 2 plus on the solution. On the other one, we have zinc and zinc 2 plus in the solution. And electrons always go from anode to cathode. And according to the shorthand, I always put the anodes first. So they're going to go from anode to cathode. So my cable, So my cable is going to be connected there. My multimeter will go on the center. And my electrons are going to travel from anode to cathode. But those electrons are not going to go anywhere unless I have a salt bridge. The salt bridge is what's going to complete the circuit. So this is a shorter way of giving you all that information. So you can say that the reaction that is happening is zinc reacting with copper 2 plus, the first term on each side, producing zinc 2 plus and copper solid. And if you know the reduction potential of this one, and you know the reduction potential of this one, then you can do the voltage of the cell. It's going to be the reduction potential of whichever is the cathode minus the anode, and which is the one we did before, which is going to give us 1.10 volts by using the tables. And by the way, this represents the salt bridge. It's what separating but bringing together at the same time the cells. So here's your first daily work. Using this, and that's not fair because I did that by just brainstorming. So try not to look at the notes and see if you can do it yourself, and then check your answers by using the note. Make sure you truly understand this. Just go ahead and draw it. Looking at that shorthand notation, remember that this is your salt bridge. Go ahead and put 2 bars in there. Tell me which one is copper, which one is zinc. Make sure that you have an aqueous solution with the corresponding cations. Tell me which one is the anode, which one is the cathode. Show me how the electrons, which directions the electrons are moving, from what metal to what metal. Put the voltage on the voltmeter once you calculate the cell potential. And everything that you saw on this lecture, see if you can capture it there. And see, this is the one we did. Try to do it on your own first, like I already said, and then verify it against the recording. And there's a lot more practice problems on the textbook that you can work on. And with that, we define most of the important terms associated with electrochemistry, and we discuss how to build a galvanic cell. And I told you the only thing I want you to worry for now about electrolytic cells is that they do not produce energy, they require energy to get the chemical reaction going. That usually happens when you don't have an spontaneous reaction, like copper losing electrons to zinc, and you're forcing it to happen. So it's not a spontaneous reaction. So with that said, we come to the end of this part. When we come back again, we're gonna see how we determine the standard and non-standard cell potentials, which I already showed you. The cell potential is nothing more than E of the cathode minus E of the anode. And you know where those numbers are coming from. So most likely we already did this part because I couldn't help myself. So that's it for right now. Let me know if you have any questions. Bring all those questions to the workshop. We got about 2 more lectures to go on this chapter.